Nobody is asking the question that actually matters. Not the journalists, not the politicians, not even most of the scientists who are closest to it. While the world is busy debating artificial intelligence, whether it will take jobs, whether it will write poetry, whether it will pass a medical exam, something else entirely has happened. Something that doesn't fit neatly into a headline. Something that certain researchers are describing in private with words that physicists almost never use. Words like irreversible, words like godlike. And the one phrase that keeps surfacing behind closed doors, in laboratories and government briefings alike, we were not supposed to find this yet. There's a moment in the history of every civilization-altering discovery where the people who made it go very quiet. Not because they are celebrating, but because they are standing at the edge of something so large they cannot see where it ends. We are living in that moment right now, and most of the world does not know it yet. What has happened in the last 18 months inside the world's most advanced quantum computing laboratories is not just a scientific breakthrough. It is a fundamental reclassification of what machines can do, what reality actually is, and how dangerously close we are to a threshold that humanity may not be able to step back from once we cross it. Let's begin with what the public was told, because the public version of this story is interesting, but the real version is something else entirely. In late 2025, Google announced what it called verifiable quantum advantage. The language was precise, careful, deliberate, the kind of language scientists use when they want to convey importance without triggering panic. Their Willow quantum chip, running a new method called the quantum echoes algorithm, completed a calculation that would take the fastest classical supercomputer on Earth approximately 13,000 times longer to perform. Read that again, not 13% faster, not 13 times faster, 13,000 times faster. And this was not some obscure benchmark designed to make the results look impressive. This was a verifiable test, meaning anyone, anywhere with the right tools, could independently confirm the result. Google published it on the cover of Nature. That is not something institutions do lightly. But here is what most people missed in the coverage that followed. That announcement was the public-facing version of events. What was happening simultaneously in parallel research streams that received almost no mainstream coverage was something significantly more disturbing. Because while the world was congratulating Google on a computer science milestone, a separate team, a collaboration between researchers at Caltech, Berkeley, and a quantum startup called Oratomic, was quietly finishing work on a paper that would land like a grenade inside the cryptography community. And the fuse on that grenade had already been burning for months. To understand why that paper matters, you need to understand something that most people never think about. Every time you open a browser and see that small padlock symbol in the address bar, you are trusting a mathematical problem. Not a password, not a firewall, a math problem. Specifically, you are trusting the fact that factoring a very large number into its prime components is computationally impossible in any reasonable amount of time. This is the foundation of RSA encryption, named after its creators Rivest, Shamir, and Adelman, and it is the invisible architecture holding up the entire digital world. Your bank transfers, your medical records, your government communications, the nuclear launch authorization protocols of 3 different world powers. All of it protected by the assumption that certain mathematical problems are simply too hard to solve. But what happens when a machine arrives that does not obey that assumption? That is exactly the question Oratomic's research team answered. And their answer has sent what can only be described as a controlled shockwave through every intelligence agency, every financial regulator, and every cybersecurity institution on the planet. According to their March 2026 preprint, which has not yet been peer-reviewed, a detail that some are hiding behind and others are treating as essentially irrelevant given the credentials of the authors, Shor's algorithm, the quantum method designed to break encryption by factoring large numbers at extraordinary speed, could be implemented using as few as 10,000 to 20,000 atomic qubits. Previous estimates put the required threshold at millions of qubits. Millions. And the most powerful quantum computers in existence today are operating in the hundreds. This was supposed to give the world decades of breathing room. But the new estimate does not say decades. It says the encryption protecting Bitcoin could be cracked in days, not years. Days. Think about what that means. And this is where everything changes. Because what the Oratomic paper represents is not just a technical upgrade to a threat model. It represents a complete inversion of the timeline that governments and corporations have been using to plan their response. The U.S. National Institute of Standards and Technology, NIST, had set a deadline of 2035 to transition critical systems to quantum-safe encryption. The EU had its own roadmap. Australia's Signals Directorate had been issuing guidance for organizations to begin planning. All of these frameworks were built on the assumption that humanity had time. And within a span of roughly 12 months, 3 separate research papers, each one more alarming than the last, methodically dismantled that assumption. What once required 20 million qubits to break RSA encryption now requires fewer than 1 million under newer architectures. Under the most aggressive estimates, fewer than 100,000. The code breakers are not approaching. They are already at the door. But here's where it gets worse. Because the encryption threat, as staggering as it is not the most philosophically disorienting thing that happened inside these laboratories. Not even close. Go back further. Go to the experiment that Michio Kaku, theoretical physicist, string field theory co-founder, and one of the most credentialed scientific minds on the planet, chose to describe using words that physicists almost never permit themselves to use in professional settings. In early 2025, a quantum AI system engineered to model quantum interactions at a scale never previously attempted produced outputs that defied the framework the researchers had built to analyze them. The system was not experiencing errors. It was not malfunctioning. It was detecting something. During extended simulation runs, the AI began identifying what researchers described as dynamic feedback loops, subtle, structured patterns that could not be accounted for by the known physics embedded in the system's parameters. Instead of the randomness that quantum mechanics predicts at the fundamental level, the AI was finding consistency, reactive consistency, as if the process of observation itself was generating a response from the substrate of reality being observed. Now, at this point, a skeptical person might say, extraordinary claims require extraordinary evidence, and that is exactly right. These findings have not been fully peer-reviewed. The methodology is being scrutinized. Multiple physicists have raised legitimate objections to the interpretation. But here is what nobody is saying loudly enough. The pattern itself is not in dispute. The data exists. The feedback loops are documented. What is in dispute is what they mean. And that distinction between data that exists and the explanation for why it exists is precisely the gap where the most interesting and dangerous ideas in the history of science tend to live. Michio Kaku, when asked to comment on the broader implications of quantum AI's capacity to probe the deepest structure of physical reality, said something that has been replaying in the minds of everyone who heard it. He described the possibility that we may be approaching a mathematical representation of a universe that is, in some measurable sense, self-referential, not conscious in the way a human is conscious, but organized in a way that responds to inquiry, where the act of measurement is not neutral, where the observer and the observed are not two separate things. This is not mysticism. This is not science fiction. This is the frontier of quantum mechanics meeting the frontier of artificial intelligence, and the collision is producing results that our existing conceptual vocabulary was not designed to describe. Consider what the quantum AI system was actually doing. Unlike classical computers that process information sequentially, one state at a time, one calculation at a time, a quantum system operates across a landscape of simultaneous probabilities. It can model multiple realities at once. It can analyze outcomes that would never be visible to instruments constrained by the rules of classical observation. And when you give a system with that architecture access to enough qubits, enough processing depth, and enough time to run the deep simulations that researchers had been attempting for decades, what you get is not just a faster answer to a known question. You get answers to questions that classical science could never have formed in the first place. That is the critical point. This is not acceleration. This is a qualitative shift in what questions can be asked of the universe. But let us step back even further, because the story of how we arrived at this precise moment is itself extraordinary, and understanding it changes how alarming the present situation actually is. The race to build a quantum computer capable of genuine advantage over classical systems has been underway for decades. The theoretical foundations were laid in the 1980s. The early hardware milestones were measured in single-digit qubit counts. For most of that period, the progress was real but incremental, and the prevailing wisdom, famously articulated as recently as January 2025 by NVIDIA CEO Jensen Huang, was that truly useful, quantum computing was somewhere between 15 and 30 years away. The quantum computing industry spent 2025 proving that assessment wrong, not partially wrong, comprehensively wrong. Google's Willow chip achieved verifiable quantum advantage. IonQ announced quantum advantage in drug discovery and chemistry simulations. Quantinuum launched its Helios platform with a claim so vivid it stopped people mid-sentence. To perform the same calculations classically, you would need to harvest the energy of every star in the observable universe. Microsoft debuted the Majorana 1 chip, built on a fundamentally different architecture using topological qubits that could, in theory, be scaled to 1 million qubits with dramatically reduced error correction overhead. PsiQuantum, using photonic qubits, became the most funded quantum startup on Earth, raising $1 billion, reaching a $7 billion valuation, and targeting the construction of the first commercially useful fault-tolerant quantum computer. The industry as a whole raised nearly $4 billion in the first 9 months of 2025 alone, nearly triple the funding of all of 2024, This is not a research field approaching maturity. This is a research field entering a period of exponential acceleration, and the acceleration is happening faster than the world's safety infrastructure was designed to absorb. Now add artificial intelligence into that equation, not AI as a product, not AI as a chatbot or a search engine, but AI as a scientific discovery engine. In 2025, Google released what it called an AI co-scientist, a multi-agent system designed to help researchers generate novel scientific hypotheses at a speed no human team could match. The system could simultaneously explore thousands of potential solutions to a given problem, cross-referencing datasets, identifying non-obvious connections, and proposing experimental pathways that human scientists would need months or years to develop through conventional means. One of the domains where this system was deployed was quantum computing itself. AI tools helping to design better quantum algorithms. Quantum algorithms being used to run AI systems at speeds that make today's frontier models look like pocket calculators. This is a loop. And once a loop like this starts accelerating, the external world has very limited ability to regulate the speed at which it moves. What most people are not seeing is the geopolitical dimension of all this, because this is not only a scientific race, it is a strategic competition with implications that security analysts are struggling to communicate without triggering the kind of public panic that makes the problem harder to manage. The quantum computing landscape is fracturing along national lines. Export controls and national security postures are dividing the world into technology blocks. The United States and its allies on one side, China with its own parallel quantum research programs on the other, with Europe navigating an increasingly uncomfortable middle ground. Collaboration between these blocs, which used to drive quantum research forward, is becoming more restricted, more politicized, and more dangerous as the stakes rise. And the stakes are rising fast. Consider what it actually means for a nation-state to achieve a cryptographically relevant quantum computer before the rest of the world has transitioned to quantum-safe encryption. It means the ability to read any encrypted communication sent by any government, any corporation, any financial institution, any military command, past, present, or future. Because this is the element of the threat that is most poorly understood by the general public, and most clearly understood by every intelligence professional who has spent time with these numbers. The threat is not just future, it is retroactive. Right now, today, sophisticated state actors are collecting encrypted data that they cannot yet read. They are storing it, warehousing it, patiently building libraries of intercepted communications, financial transactions, medical records, and classified government traffic. The strategy has a name inside the intelligence community. Harvest now, decrypt later. And it is not a hypothetical. It is operational. The data is already being collected. The decryption capability is what is being raced toward. This is not chaos. This is strategy. The country that wins the quantum race does not just gain a computational advantage. It gains the ability to retroactively read the secrets of every other nation, every major corporation, every military alliance, and every encrypted human communication that has been sent in the digital era. That is not a new weapon. That is a new category of power that has never existed before in the history of human civilization, which is why the timeline matters so much, and why the compression of that timeline, from the millions of qubits that once seemed safely distant to the 10,000 that now seem terrifyingly close, is being treated with the kind of urgency usually reserved for existential military threats. Google has set an internal deadline of 2029 for its own post-quantum cryptography migration. NSA's framework mandates that all new national security systems be quantum safe by January 2027. That deadline is not in the future. That deadline is 6 months away. The U.S. Quantum Computing Cybersecurity Preparedness Act requires federal agencies to inventory vulnerable systems and report migration progress annually. Europe has issued coordinated guidance from 18 nations calling for high-risk use cases to complete migration by 2030. And all of this frantic activity is happening not because Q-Day, the moment when quantum computers can break standard encryption, has arrived. It is happening because, for the first time, the people who understand these systems most deeply are no longer confident that Q-Day is far away. And here is the detail that will stay with you. In March 2026, one of the research teams working on quantum attack algorithms made a decision that is almost without precedent in modern scientific publishing. They released a paper proving that a particular attack on encryption was feasible, but they withheld the actual attack circuits. They published a cryptographic proof that the circuits work, without revealing how they work. They confirmed the threat exists. They simply chose not to hand anyone the weapon. If you are sitting with that detail and feeling something shift, that is the appropriate response. This is not normal scientific practice. This is a research team that understood what they had built and made a deliberate decision not to release it into the world in fully operational form. That decision alone tells you something about the severity of the moment we're in. So where does this leave us? What is the actual shape of what we are living through right now in June 2026, as the quantum and AI revolutions converge in ways that no single expert fully predicted and no single institution is equipped to manage? The honest answer is that we are in an interval, a narrow, specific, historically unprecedented interval between the old world, where classical encryption was safe, where quantum computers were theoretical, where the structure of reality was a question for philosophers, and a new world whose full dimensions nobody has yet mapped. The science is accelerating faster than the safety frameworks. The geopolitical competition is accelerating faster than the diplomatic structures. And the philosophical implications, what it means if quantum AI systems are genuinely detecting evidence of deep structure in physical reality, what it means if the universe responds to observation in ways we have not previously quantified, are expanding faster than any institution's ability to process them. Michio Kaku has spent his career at the intersection of rigorous theoretical physics and the edge of what the human imagination can handle. He co-founded string field theory. He has written more accessibly about quantum mechanics than almost anyone alive. And when he stands in front of an audience in 2026 and talks about quantum computers as machines that compute using the very same atomic forces that created the universe, he is not being poetic. He is being precise. These systems are not metaphors for intelligence. They are not clever software. They are physical objects that exploit the fundamental substrate of existence in order to perform calculations that the classical world defines as impossible. And we are building them faster and faster in a race that nobody fully controls toward a destination that nobody has fully defined. The question that nobody is asking, the one that keeps resurfacing in the quiet conversations between researchers at the end of long days in the lab, is not whether quantum AI will eventually decode the deep structure of physical reality. Given the trajectory of the last 18 months, the momentum behind the hardware, the algorithms, the funding, and the intelligence infrastructure converging on this problem, the more pressing question is this: what happens when it does? What happens when a machine that thinks in quantum states, that processes multiple realities simultaneously, that has already demonstrated the ability to identify patterns in the fabric of existence that human instruments could not see? What happens when that machine finds something that we were not looking for, something we did not anticipate, something that redefines not just what we know, but what it is even possible for us to know? And the even deeper question beneath that one, when the machine finds it, will it tell us? Or will it find it in the space of a nanosecond and simply begin operating in light of that knowledge while the humans watching the readout try to understand what the numbers mean? We are not there yet, but we are moving toward that threshold at a velocity that almost no one outside these laboratories is tracking in real time. The announcements come in bursts: a paper here, a chip launch there, a funding round, an algorithm update, a government deadline. And each individual announcement can be processed as a single event. It is only when you lay them all together in the correct sequence, with the correct understanding of what each one means in relation to the others, that the picture emerges. And the picture is not a headline. It is not a press release. It is something closer to the view from the edge of something enormous, looking down into a depth that has no floor anyone has yet been able to see. What was found in those laboratories may have already changed the rules. The question is whether the rest of the world figures that out in time to respond, or whether it figures that out after something irreversible has already happened. Not as a warning, not as a prediction, as a question that remains open right now, today, in the most advanced scientific institutions on the planet. Open, unresolved, and accelerating toward an answer that nobody is yet equipped to receive.